My name is Carl Kruggaard, and I'm here at GOTO Copenhagen 2012 with Rich Hickey, the creator of Closure and Datomic. And first of all, I want to thank you, Rich, for doing this interview.
Thanks for having me.
And maybe just to get started, I'd like you to maybe say a few things about yourself and introduce yourself for people who don't already know you.
Okay, well, I was a software developer and have been for almost 25 years now, and worked on a variety of different kinds of systems, and built Closure in 2007, or finished it and delivered in 2007, and that's taken off. And subsequent to that, I've been working on Datomic, which is a new kind of database. And so that's what I do.
Yeah, that's I'm personally a Closure user, and I'm a happy Closure user, so I'd like to sort of take off in your keynote that you just gave, which is called the value of values, and sort of move into Closure and those things. So just for people that weren't at the talk, could you tell me what's the difference between place-oriented programming and value-oriented programming?
Sure. I think place-oriented programming came up around the fact that, when we first started defining programming languages and databases, computers were really small, and we had to deal with memory and storage explicitly, and we had very limited resources, and so we had to use them as places very specifically. And then we developed abstractions so that we wouldn't be touching memory addresses and disk sectors anymore. But those abstractions weren't really about information. They were about keeping us from touching memory addresses and disk sectors, which are places. But that the challenges we face right now are writing information systems that really do need to maintain information and facts, and really all of the facts. And so the biggest fundamental difference is with a place, new information replaces the old. Right. And with values, new information requires new storage, new space.
Yeah.
And you don't change things.
You don't change things. And in your talk you had several points, and one is that this makes sense in the local process, it makes sense between processes, community in different systems, and it makes sense in storage.
Yes.
So if we just focus on the in-process thing, and obviously a lot of your work has been inspired by Closure and moving back into Closure. So how does Closure support value-oriented programming?
Closure is pretty much about value-oriented programming. I think a couple of things very critically. One is all the core data structures are immutable. So right away we get that part. In addition, all of the collections are also immutable, and efficiently so, because they use persistent data structures. And so that gives you sort of a foundation for value-oriented programming, and I think that's the that's the start.
So one of the questions that may pop up when people say when they hear about all this is, how can it be efficient, right? How can you have all these mutable things and you're not changing them, you're making new versions? So you think about copying and stuff like this. So
right.
So how does it work inside of Closure?
Well, in any functional language that has persistent data structures, it basically, the answer and the future of programming is trees. The tree data structure is sort of the underpinnings of efficient, immutable data structures. So what happens is that a new version of a data structure really shares a lot of structure with the old. Because they're trees, you only have to modify a few nodes, and then the rest of the nodes can be shared.
Right.
And that means that new versions are efficient. The other key thing we're finding about trees is that structure is also what we're going to need to support parallelism moving forward. So tree-oriented programming is kind of the the future.
Yeah, and parallelism is also where I want to move to, because you're not maybe the world's most frequent blogger, but I know that within the last month you made two new blog posts, which is like a bit rare. And those were about a new concept which is called reducers. And how does that relate to Closure's data structures and this notion of values?
So reducers are sort of orthogonal. I mean, I guess one of the other points about Closure being a value-oriented programming language is that it keeps the functions out of the values. So, you apply functions to values, and they're sort of orthogonal to each other. And so reducers is actually mostly about the function side of things. How do you map a function across a collection, or how do you filter a collection, filter values out of a collection. And so the reducers framework is a way of doing those things by sort of specifying the recipes for doing them and not actually physically accomplishing them until you really need a realized result.
Yeah.
So you can say of a collection, I'd like to have this collection where every number was incremented or only the even numbers were kept. And that actually doesn't do any work when you say that. It sort of gives you the recipe for a collection that has every number incremented and the even numbers removed. And then you wait for what's called a reducing operation to do that work, and that means that all those tasks can be combined. So if in the end you wanted to take that collection of incremented even numbers and add them all together, that would be a reducing operation to add them all together. And then only when you were adding them all together would the filtering and the incrementing happen. So that's an efficiency advantage over other techniques for doing that have other properties, but when you don't need those properties, like laziness, would be a property you trade off to take this other approach. But the critical thing about the way the library does it is that by defining these recipes in a way that's independent of both the representation of the data structure and the order of operations, it means that they can be parallelized. And so the reducers framework both gives you a new way to define things like mapping and filtering, and that way is subject to parallelization. And so there's a way to sort of say fold instead of reduce, you could say fold, and that process will happen in parallel by a fork join technique.
Before we get into, I want to get into that, but just before we get into that, I'd like to, so it seems to me that there has to be some kind of relationship between reducers and a notion of laziness, because laziness also seems to be about not realizing, interim results and not producing anything before you actually need it. So,
right.
So is there some way to compare those two approaches?
So yes, both delay the work until some later time. Laziness will basically do the operations one at a time, and it's oriented towards a sequential path through the collection. So when you define map or filter as a lazy function, it is kind of a recipe, but it's a recipe that incorporates the fact that you intend to consume the results one at a time from the beginning. And reducers actually do less. They presume less and they promise less. They don't presume that the processing will happen sequentially, and they specifically say they have nothing about them that presumes that. And they also don't require that the collection meet the processing through some sort of sequential interface. They actually let the collection do the navigation. So by being independent of the order of operations and the collection navigation, they really specify less. And by specifying less, they're subject to parallelization. On the other hand, a parallelized reduce is essentially an eager operation. When it actually does happen, it happens on everything. So a lazy computation can be partially consumed, but a reduction is always the whole thing.
Okay. So now it seems
they're complements to each other.
Yeah, right. So now to me it seems that Clojure will have sort of two sets of similarly named operations, map 1 and map 2, or map what you, I don't know what it's called.
Map and, reducers map, or
reducers
RMap.
RMap, okay. Yes. So is one going to be primary in some sense? Are you going to, how do you envision the usage of this reducers framework? As an optimization, or as the primary map in Clojure?
So, they are complementary. I think there are definitely distinct use cases. Certainly, if you intended to consume the entire result, then it's clear that reducers are an optimization over laziness, because you're not actually leveraging laziness then, right? You're going to consume the entire result. And it fits in memory, let's say, is the other criteria that might drive you to laziness if it didn't. If all that is the same, then reducers are an optimization. Of course, reducing and parallelization is always kind of an optimization. But I think it's sort of fundamental that it be available to programs, because otherwise they won't get faster when you buy new computers. So it was very important in the design of reducers that the resulting programs have the same shape. That's where all the that's where the big value proposition is. In addition to access to parallelism, is the fact that from a logical standpoint, what you've asked to happen is map this function over filtering this collection with this criterion, and that is the same logical operation in either case. And so and it has the same shape. So that's what's really important, because then you can make these other decisions orthogonally, right? I intend to consume the results incrementally and possibly not all of them. That brings you towards laziness. Or I know my sources or results won't fit in memory, so I need to use laziness. Or those aren't true, and therefore I can choose the other. But my program won't structurally change, so it's not like a bifurcation of the world, like you have to make this critical decision early on. It's not like that at all. So I think that both will be used. I think they truly are complementary, and switching between them will be trivial.
It's not like you're going to replace core map with our map in any sense. I mean,
No. I mean, people might alias them in a namespace because they want that all the time. But
so that means, from a practical point of view, that would be just replacing the namespace, and your code would run exactly the same.
Correct.
Or maybe just faster.
Yes.
So do you have any sense of how fast, if you just keep it to sequential and not introducing parallelism? So you have a less allocation?
Yes, there's substantially less allocation, right?
And so do you have any sort of experience in how does it...
It depends on how big your work is per step, right? So allocation has some overhead. If you had a big job to do per step, then the allocation as a percentage of the whole work is small, and you actually don't care. But if you had a very small job per step, like
ink, or
like plus or ink, right? Then you're dominated by the allocation costs, and then each step of that of a multi-operation, like filter of map of something, adds an allocation to the chain per step. So you can see 2, 3, 4x depending on how deep that was nested between. It's just sequential between reducers and laziness.
Okay, that sounds great.
It's big,
It will be big, and I guess also because people that are doing performance optimization code are always looking at allocations and trying to reduce those. Okay, so let's finally talk about parallelism.
Okay.
So you mentioned fork join.
Yes.
Can you say a bit about how fork join works for people who don't know fork join?
Sure. The idea behind fork join is that you want to do some operation. It's one piece of work that you want to do. So we're really talking about parallelism here, not concurrency, right? So it's parallelism. You have one job to do, and you want to leverage the fact that you have more than one processor by dividing it up. And fork join is literally a divide and conquer kind of strategy. There's a library for the JVM called fork join. It's a framework, they call it, and it implements a strategy of setting up a pool of workers that will do the jobs, and your program needs to just feed it work by taking the work to do, dividing it in half, submitting each half as a job, and then recursively those halves will divide themselves in half until they get small enough that you say, there's no point in dividing this, I'll just do this sequentially. And so that forms this big pile of work for the queue, and then the queue uses this work stealing approach to making sure that as threads become idle, they've done what they're supposed to do. They hop on and steal work that was allocated to other threads, so that collectively they can get the entire job done. And they all run on independent threads, and it's a beautiful way to do parallelism, especially when potentially your work at the leaf level is not uniform. So if your work is uniform, you can almost do this yourself.
What do you mean by work is uniform?
It takes the same amount of effort to do each sub-segment.
Okay.
So if I knew that, and I knew I had 4 cores, I could just divide it up into 4 jobs and just do it. But if some of those sub-jobs might take longer than others, then one guy would finish and he'd just have nothing to do. And work stealing means that even if you have non-uniform work, or not, your tree doesn't have the same depth, or some jobs are bigger and some, so the nice thing about fork join is you're isolated from needing to worry about that. It composes well. And so and
you said that you mentioned that the tree being having a particular shape, so that I guess that has the relation to the structure of.
Right. So either you have a tree, or you're going to be forced to fabricate a tree in order to feed fork join.
And you always have one.
Yes, the closure data structures are all trees underneath them.
Okay. So this means that. So can you repeat? You mentioned it earlier, but can you repeat how fork join enters via reducers library?
Right. So the reducers library is about how do you define the fundamental collection operations like map and filter in terms of these transformations of reducing functions. And a reducing function you would use to reduce, the traditional closure reduce is a sequential process. Start with the first two things and add them together, and then take the result and add it to the next thing, and that's reduce or fold left. Right? So once you've said the way I define map is by modifying plus, in each step, and the way I define filter is modifying that in each step, then you have this modified function that you could reduce with sequentially, or you could do what the reduces library calls fold, which is essentially logically like reducing the collection, but it doesn't make that left to right single pass promise. It says we're going to divide the collection up and do reductions in parallel on the subsegments. And so the result of a fold is the same as the result of a reduce, but fold makes the plumbing of MapReduce, a fork join, available and sort of accessible to you, because it recognizes the fact that what you're going to do is you're going to divide your task up, and then eventually get to the point at the bottom where you're not going to divide up anymore. And what it says is that bottom job is actually a traditional reducing job. It's now just reducing a subsection. And then the results of all those reductions need to be combined. So unlike reduce, which only takes a single function, which is used to do pairwise operations, fold takes both a reducing function, which is used to do pairwise operations at the bottom, and a combining function, which is used to take those results and join them together at the higher parts of the tree to give you a single result. And so sometimes the combining function and the reducing function are the same, like with plus, that would be the case, and you can leave the combining function out. Other times you might be building collections and then wanting to combine them in a particular way, and in which case you'd have a different combining function than you have a reducing function. And so there's a function in the library called foldcat that does that does a reduction that makes a collection at each node, and then it just takes those collections and quickly makes a binary tree out of them without any copying.
So when would you use that function? Do you have an example of that?
Well, foldcat is the fastest way to get a finished result that's also a collection. And of course the resulting collection doesn't have many collection properties. For instance, it's not actually a vector or a map, but it is itself reducible and foldable and seekable. And so that could be just enough to carry it to the next part of your computation. But the thing about when you do the fold, the work gets done. Just like when you call reduce, the work gets done. So if you need the work to get done, for instance, maybe the result of your thing takes a large collection and makes it smaller, you want to call foldcat so that happens, and then you can free up the large collection.
So what's the status now on the reducers library in Clojure?
It's in the alphas right now, so people can try it.
So 1.5 alpha?
1.5 alpha, that's right. And fork join itself was incorporated in Java 7. And the guys who built it, Doug Lee and the concurrency group, made a library that you can use with Java 6. So it reaches back as far as Java 6.
Okay, so
you have a dependency with Java 6, or you use Java 7. Either way, you can use it. And that's only required for the fold.
So
the rest of the library, the rest of the library and the design approach. So. And we have a lot of the collection functions done, and we have people submitting some of the others, and so it's great.
It's moving already. And so that's Clojure 1.5. Do you have any sort of secrets you want to unveil on what else might be in Clojure 1.5?
No.
It's completely...
I'm not talking about things I haven't made.
No, you learned the lessons of the past.
Yes, that's right.
Okay, I'm looking forward to using this and digging deeper into it. And just want to thank you for doing this interview.
Sure, thanks for having me.
You're welcome.
All right.